Okay. Assalamualaikum warahmatullahi taala wabarakatuh. My name is Ahmad Zahir Razi Bizulkifli. My matrix number is CD240358. Okay, for the introduction, why most people think of material strength in terms of pulling things apart, torsion testing gives us a much more nuanced look at how a material actually behaves. By twisting a specimen at constant speed and measuring the torque it generates, we can then directly find the shear modulus. Why does this matter? Because G is the secret key to find Young modulus using the relationship E equal to G1 plus V. We can see that these two properties are actually proportional. By measuring how a material resists a twist, we aren't just looking at one specific behavior, we're validating the entire elastic blueprint of the material.
Assalamualaikum and a very good day. My name is Nurul Irdina binti Muhammad Akram. My matrix number is CD240184. So here is the background study of our group project. Torsion. Torsion occurs when a moment couple causes by structural member to rotate it about its longitudinal axis. Torsional loading is also commonly found in components such as drive shaft, axles, and drill bits.
Hi, Assalamualaikum. My name is Nur Patricia binti Zulkifli and my matrix number is CD240048. Today, I want to explain about the problem statement in our group project, which is torsion test analysis the specimen of the mild steel and brass. The first one is engineers must calculate specific torque values to ensure a component does not reach the point of plastic deformation or total failure. The next one is a major cause of design failure is the failure to verify essential material properties, specifically the shear modulus and the modulus of rupture. Then, the modulus of rupture defines the absolute maximum stress a material can endure before fracturing, serving as the critical upper limit for shear stress in torsional designs. Last but not least, design often failed when they operate too close to this failure region, particularly when the simplified calculations ignore the higher stresses caused by fluctuating or shock loading. And lastly, is a reliable design necessitates moving beyond theoretical equation by validating real material properties, applying safety factors, and accounting for actual loading.
Here is the objective, what we will learn at the end of this project. The first one, to relate the torque applied to the angle of twist. The second one, to calculate the value of the shear modulus of the specimen. Next, to determine the shear stress at proportional limit and the modulus of rupture. Last, to observe the failure patterns of different materials under torsion. So here is the experimental procedure. They are divided into 6 procedures that we must follow during the experiment. Number 1. Measure specimen dimension. Record all the value that we measure. Number 2. Mount specimen. Ensure the horizontal alignment and make sure the specimen is clamped at the torsion testing machine. Number 3. Set angular indicator. Set initial reading to 0. Attach the specimen and see the angular at the indicator. Number 4. Apply load. Add load incrementally and record the angle of twist at each load applied. Number 5. Unload the specimen. Gradually remove the load and also record angle of twist during the unloading. And lastly, number 6, repeat for the second specimen, because for this project, we use 2 specimens, mild steel and brass.
For the next presentation, I will explain the result obtained from the torsion test experiment focusing on displacement dimension and the torsional behavior of brass and mild steel shaft. First, I will explain table 1, which shows the diameter and length measurements of the test specimen. For each shaft, the diameter was measured 3 times to reduce error and an average value was calculated. For the brass shaft, the measured diameters are 6.14 mm, 6.13 mm, and 6.09 mm, giving an average diameters of 6.12 mm. The lengths measured are 2.99.53 mm, 2.99.21 mm, and 2.99.6 mm with an average length of 2.99.40 mm. For the mild steel shaft, the diameter are 6.21 mm, 6.13 mm, and 6.17 mm with an average diameter of 6.17 mm. The lengths recorded are 2.99.83 mm, 301.24 mm, and 301.10 mm, resulting in an average length of 300.73 mm. The pulley length used in the experiment is 45 mm. These average values are later used in the torsion calculations. Next, I will explain table 2, which shows the torsion test results for the brass shaft. The applied load was increased from 0 Newton to 200 Newton and the corresponding angle twist was recorded. During addition of load, the angle of twist increased from 0 degree to 16 degree as the load increased. During removal of load, the angle of twist values were slightly different, starting from 4 degree and reaching 16 degree at maximum load. This difference between loading and unloading indicates the presence of elastic hysteresis, which is commonly observed in ductile materials like brass. From the brass shaft result, we can observe that the angle of twist increased with applied load. The relationship between load and twist is approximately linear within the elastic range. Brass shows a larger angle of twist, which indicates that it is less stiff compared to mild steel. Now moving on to table 3, which present the torsion test result for the mild steel shaft. The load range is the same, from 0 Newton to 200 Newton. During addition of load, the angle of twist increases gradually from 0 degree to 8 degree. During removal of load, the angle of twist values are 0 degree, 3 degree, 5 degree, 7 degree, and 8 degree. The difference between loading and unloading is smaller compared to brass. From the mild steel results, we can conclude that the angle of twist is significantly smaller than brass for the same load. This shows that mild steel has higher torsional stiffness. Mild steel undergoes less deformation, indicating a higher modulus of rigidity. When comparing both materials, brass shows larger angular deformation, meaning it is more flexible. Mild steel shows smaller angular deformation, meaning it is stiffer. Both materials follow the expected torsion behavior where angle of twist increase with load. In conclusion, the experimental results are consistent with torsion theory. The measured dimensions allow accurate calculation of torsional properties. Brass exhibits higher angular twist, while mild steel demonstrate higher rigidity. The experiment successfully achieved its objective. That concludes my presentation. Thank you. In this part, I will presenting the torsion test calculation and final results obtained from the laboratory test. The purpose of this torsion test is to study the behavior of a circular shaft under torsional loading and to determine important mechanical properties such as shear stress, angle of twist, and modulus of rigidity. To calculate the torsion, we use the T equal to force multiplied by radius. Then the shear modulus, G equal TL over J angle of twist, where T is applied torque, L is length of specimen, J is polar moment of inertia. Polar moment of inertia. For a solid circular shaft, the polar moment of inertia is calculated using J equal pi d power of 4 divided by 32. This value is essential as it represents the shaft's resistance to torsion and is used in both shear stress and angle of twist calculation. Using the experimental data, the value of J is first calculated. Number 2, the applied torque T is substituted into the shear stress equation. Number 3, the maximum shear stress is determined at the outer radius. Number 4, the modulus of rigidity G is calculated by rearranging the angle of twist equation.
While the math gives us a perfect baseline, our lab result revealed the true personality of this material in action. By applying a 200 Newton load, we saw a clear divide. Brass proved much more flexible, twisting to 16 degrees, while my steel stood its ground at just 8 degrees. This physical difference translates to a shear modulus of 9.31 gigapascal for steel, nearly double the 4.76 gigapascal we calculate for brass. However, the experiment also highlights the reality of hysteresis. We noticed that once that load was removed, the materials didn't immediately forget the stress. The brass specimen, for instance, had a 4-degree residual twist. This variation between the loading and unloading phases likely caused by internal friction or the limit of manual indicator. Remind us that real-world engineering requires precision tools like digital encoders to capture the full story beyond the textbook formula. Okay, to rack steam up, let's look at how these materials actually perform in the lab. We tested two shaft brass and mild steel, both with a diameter of 6.1 millimeter. The real difference showed up when we hit the 200 Newton load. The brass specimen twisted significantly, reaching 16 degrees, while the Studio mild steel only turned 8 degrees. When we translated that into the shear modulus, the math back up what we saw. The mass still had a rigidity of about 9.31 gigapascal, which is nearly double the 4.76 gigapascal we found for brass. We did notice a tiny bit of lag when we took the weight off, specifically a 4-degree residual angle in the brass, which was likely just friction in the machine. But overall, the data is clear. If you need a material that can resist a twist, mass steel is the far superior choice.